All right, let's dive right in. We're going to peek inside a flame and find something that honestly just shouldn't be there. It kind of breaks the rules we thought we knew.
So you think you know how fire works, right? I mean, it's simple. Heat goes up, flames go up. End of story. But what if it didn't? What if I told you that scientists found a flame where the fuel was actually swirling backwards, kind of curling down against the flow? Yeah, it's a discovery that really messes with our basic understanding of fire.
Deep inside the fuel stream, they found this bizarre little vortex spinning in the opposite direction it should be. It's a real head-scratcher. So in this explainer, we're going to follow the clues, just like a detective story, to figure out exactly what's going on with this strange flame.
Okay, let's get into the nitty-gritty. What did this thing actually look like? And more importantly, why was it such a puzzle for the researchers who first saw it?
So picture this. You've got fuel coming out of a nozzle, and you expect it to just go straight up, right? But that's not what was happening. The very center of that fuel stream was, well, it was curling back on itself. It was creating this little whirlpool, this recirculation zone, as they call it. It's the last thing you'd expect to see inside a flame. And this is the quote from the actual scientific paper. You know, it sounds pretty dry and academic, right? A recirculating flow pattern. But for people who study combustion for a living, finding this was like finding a footprint on Mars. It was a huge signal that something totally new was going on. And just like that, the mystery was on.
All right, so every good mystery needs a clue. And the first big one came when they noticed which fuels were causing this weird effect and which ones weren't. This pointed them directly at a prime suspect.
And here's the million-dollar question. Why did the vortex show up every single time with heavy fuels like propane and butane? But, poof, it was gone when they used a light fuel like methane. I mean, methane is basically natural gas. This wasn't just some random fluke. This was the clue they needed to crack the case.
So their big idea came down to one concept: negative buoyancy. Now, that sounds super technical, but trust me, it's not. All it really means is that the fuel itself, the gas, was heavier than the air around it. So think about it. You're pushing this heavy gas up, but gravity is constantly trying to pull it back down. A classic tug of war.
And this comparison really lays it all out. Look at methane. It's super light, way lighter than air. It's like a helium balloon. It just wants to float up. But then you look at something like N-butane. Wow, it's almost twice as heavy as air. It's more like a rock than a balloon. It wants to sink. So even though it's being shot upwards, its own weight is fighting to drag it down. And that was suspect number one for causing that weird vortex.
Okay, so to prove this wasn't just a theory, they came up with a really clever experiment. They started with 100% pure methane, no vortex as expected. Then they slowly started blending in the heavy stuff, N-butane, making the fuel mix just a little bit heavier and a little bit heavier until, bam! The vortex just appeared out of nowhere. It was brilliant, because it let them find the exact tipping point, the precise density where things got weird.
But, you know, science is never that simple. They quickly realized that the fuel's weight wasn't the only thing that mattered. There was another piece to the puzzle, another force in the fight, creating this constant battle right there inside the flame. And it all came down to this epic showdown between two forces. On one team, you've got negative buoyancy. That's gravity, just pulling that heavy fuel straight down. And on the other team, you have jet momentum. That's the raw upward push from the fuel jet. The vortex? Well, it's basically the sign that tells you which team is winning.
Okay, get this, because this is where it gets really cool. Check out the table. You take a heavy fuel mix and shoot it out slowly, and yep, the vortex is there. Gravity wins. But then you take that same exact fuel and just crank up the speed, push it out faster, and the vortex is gone, momentum wins. But then, and this is the kicker, look at the last row. If the fuel is super heavy, even that higher speed can't save it. Gravity comes roaring back and takes the win.
So what this all means is that the upward push can absolutely beat the downward pull, but only up to a point. It's a constant struggle. If the fuel is heavy enough, or if you're not pushing it hard enough, gravity is going to win that fight every time. And that's when you get the vortex. All right, so the pieces were all on the board. They knew about the forces, they knew what was happening, but they needed to put it all together. They were looking for that one magic formula, that one number that could predict whether the vortex would show up no matter what.
And that was the final boss battle. Really? How do you take all these different things, the weight of the fuel, the weight of the air, the speed of the jet, and combine them into one single predictive number?
They needed something that would just spit out a yes or a no for the vortex, for any situation you could dream up.
And they found it. They took a classic concept from physics, something called the Richardson number, and they modified it for their specific problem. You can think of this modified number, ρ, as the final score in that tug-of-war match. It tells you, plain and simple, who won, gravity's pull or the jet's push.
So after running all the tests and doing all the math, they found the magic number, the tipping point. And it wasn't something obvious like 1 or 100. The number was 60, roughly 60.
And this chart just makes it so beautifully simple. They figured out a clear rule. If that ρ number is less than 60, momentum wins. No vortex, but the second it tips over 60, boom, gravity takes over, and the vortex shows up. Just like that, the mystery was solved. So elegant.
Okay, so great, we solved the tiny flame mystery, but who cares, right? Why does this little backward swirl actually matter in the real world? Well, it turns out the implications are actually kind of huge.
Yeah, this is way more than just a neat science trick. For one, that vortex is great at trapping soot, which could help us make engines that pollute less. It also acts like a natural flame holder, keeping the fire stable without any extra parts, which is a huge deal for things like jet engines. And on a bigger level, understanding this just gives us a deeper, better model of how fire actually works, which helps us design all kinds of better technology.
And really, this one sentence from the researchers wraps up the whole investigation perfectly. The negative buoyancy was the driving force, the bad guy, if you will, and the jet momentum was the hero trying to stop it. What a perfect summary. So, this whole thing leaves us with a really exciting question. Now that we understand this weird backwards flame, can we use it? Could we actually engineer this vortex on purpose to build cleaner, more stable, more efficient engines for the future? That's the next big question, and it's a pretty exciting one.